welcome to the naming and drawing of hydrocarbon molecules. It's going to be very important that during today's notes that you're able to look at reference table P and reference table Q. I'm going to start by talking about types of formulas. I'm going to use the example of pentane. If you're looking at table P right now, you'll see that the prefix pent means 5. Most of the time we're going to draw complete structural formulas. So a pentane molecule will have 5 carbons in a row. And as we discussed in our last video, each carbon can hold 4 bonds. So where there isn't another carbon bonded, there's going to be a hydrogen. And we'll discuss this a little bit more in detail, but I just want you in this particular portion to understand what an actual structural formula is. A structural formula shows exactly how these atoms are laid out in the molecule and how they're bonded together. Then we can write something called a condensed structural formula. In a condensed structural formula, each of these portions is broken down. So instead of drawing the C with the 3 H's on it, we condense that down to CH3. Carbons in the middle, because they're bonded to other carbons, have lots of room for H's. So we have CH2, 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 and CH3 on the end. This still shows us that these carbons are bonded in a row, and we actually could show things like branching that we might need to show, but it does make this a little bit easier to write in a smaller space. Many of the questions that you see on tests and quizzes will utilize condensed structural formulas. Last but not least, we have a molecular formula. If we count our number of carbon atoms, 1, 2, 3, 4, 5, and we count our number of hydrogens, 3 plus 2 is 5, 6, 7, 8, 9, 10, 11, 12, we can condense this down to the molecular formula C5H12. This tells us a lot in terms of if we need to calculate something like gram formula mass, but we might have a molecule that looks like this. This is what's called a branched chain alkane. The problem with the molecular formula is if you were to actually count these, we have 5 carbons, 3, 4, 5, 6, 7, 8, 9, 10, 11, I forgot that guy, 12 hydrogens. It's exactly the same. These are actually 2 different molecules, which is something we'll talk about later. So this formula, the molecular formula, really doesn't give us quite as much information. I apologize about that. Okay. I have given you the steps written out in your notes. We're going to break these down one at a time and go through what they actually mean. Step 1 is to identify the longest carbon chain. This is the most carbons in a row. In this particular example, all the carbons are very clearly in a row. We don't have any branching. I've also shown you the condensed structural formula for the same molecule, just so you have the chance to see it. We're going to number that chain. And we like to actually number in both directions. The reason that we like to do this is sometimes we're going to have to tell people where certain things are, and the orientation of the molecule can be kind of important. 1, 2, 3, 4, 5, 6. Or if we number in this direction, 1, 2, 3, 4, 5, 6. It's not going to make a real difference in this particular example, but it is a nice habit to get into. Based on the number of carbons in a row, we're going to use table P to assign a prefix. 6 carbons in a row is the prefix hex. Next, we look at our bond type. This molecule has all single bonds. I don't see any double or triple bonds. So now I'm going to go to table Q. And when I have all single bonds, if I look at those sample structural formulas, single bonds are the alkanes. And they have an ane ending. Sometimes we have something called substituents. And I did give you a little table of these. We don't actually have any in this particular example. So for this example, you can cross that out. Now we're going to put it together. Our prefix is hex. Our suffix is ane. That molecule right there is hexane. So now let's look at an example that does have a substituent. So if we look at our longest carbon chain here, we're going to notice that there's actually something coming off this called a branch. So it's called a branched chain alkane. And you can look at your condensed structural formula and see that we have shown that branch. And it's coming off the same carbon as it is in our full structural formula. So first we're going to look at our number of carbons in a row. 1, 2, 3, 4, 5, 6, 7. And I'm going to just, to show you why this is important, be numbering in the other direction. Now, because we have 7 carbons in a row, our prefix is het. Because we have all single bonds, our suffix is ane. We still have to tell people, however, about this substituent group right here. Now, we're actually going to name this group based on the number of carbons in it. This is a methyl group. In our little table over here, we've just shown this written as CH3. That's just a way of condensing down this structure. If you imagine that that's coming off of our chain. So our methyl, which is a 1-carbon group because the prefix for 1 carbon is meth, our methyl group we have to tell people about. And it is actually important to let people know where that substituent group is. We need to tell people using a number. And because this molecule has the ability to move in space, we need to make sure that there's a consistent way that we number this. So what we always do in organic chemistry is make sure that we give any substituent the lowest number possible. If we number going from left to right, this substituent would be identified as being at carbon 5. Whereas if we number from right to left, the substituent is identified as being at carbon 3. 3 is lower than 5. Which means this is going to be called 3-methyl. Once you pick a numbering order, you do have to stick to it, but most of our examples are a little bit simpler where you won't have to worry about that too much. It'll be fairly obvious. So now we're going to put it together. 3-methyl heptane. So we put our substituent group first, our 3-methyl. We told people where it was. We told people we have 7 carbons in a row, and they're attached by all single bonds. Our next molecule is 2 substituents. So if we identify first our longer chain, you'll notice we have 2 methyl groups. So my number of carbons in a row, go ahead and number this, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. My number of carbons in a row is 6, which is the prefix, hex. All single bonds is the suffix ane. Now we have 2 substituents that are both coming off of either carbon 5 or carbon 2. I'm going to select to number this so that they're coming off carbon 2 because 2 is a lower number. So instead of just telling people I have a methyl group, I'm going to tell people I have 2 methyl groups by saying dimethyl, and I need to tell people where both of them are. Each of those is on carbon 2. Every methyl that I talk about needs a number. So this is 2,2-dimethyl. Next, I'm going to go ahead and I'm going to put this together. 2,2-dimethyl hexane. I can also have another type of substituent with more carbons in it. I identify my longest chain here. I have 2 substituents. 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8. My prefix will be oct. All single bonds gives me an ane ending. One of my substituents has 1 carbon, so it's called a methyl. My other substituent has 2 carbons, so it's called an ethyl. Now once we've picked a numbering order, we must stick to it. If I number from left to right, I have my methyl at carbon 2, my ethyl at carbon 4. If I number in the other direction, I'd end up with 5 and 7, which are higher anyway. So I need to put 2 with my methyl to tell people where that goes. I people where that goes. Now, which one should you put first? You could put methyl first because it has fewer carbons in it. That's what I'm going to choose to do. It's arguable that these also should go in alphabetical order, in which case ethyl would be first. For our purposes, I would accept either this or this. It's okay if you reverse the order, but it is important to keep in mind the 4 has to be with ethyl, the 2 has to be with methyl. What if we have a double or triple bond? We first identify our number of carbons in a row. Keep in mind in this structural formula, this condensed structural formula, this is actually showing where the double bond is. And I know that because there's only one hydrogen attached to each of these carbons. So once we have this double bond over here, it's affecting the number of hydrogens that can fit onto each of those carbons. So that is shown in that condensed structural formula. So there is so it is visible that you have a double bond there, and that's an important thing to be able to recognize. First thing I'm going to do is number 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. My number of carbons in a row is pent. Now, because I have a double bond, I'm going to go to table Q. I'm going to find my example of the double bond. And these compounds end in -ene. So the ending of this molecule will actually say pentene. We don't have any branch substituents coming off, so we don't need to do that. However, we are going to need to make sure that we tell people where that double bond is. So we're actually going to write pentene, and then we are going to put a number in front of this. So we want to tell people where the double bond starts. If you number this way, the double bond is starting at carbon 3. If you number this way, the double bond is starting at carbon 2. So it's looking for the starting carbon in the direction you're numbering it. So since my bond is starting at carbon 2, I'm going to go from right to left and call this 2-pentene. Here's another example of one where we're given a condensed formula, and we have to figure out what type of bond is there. I'm going to draw this out. So my first carbon has 3 H's on it. My second carbon has 2 H's on it. My third carbon has none. My fourth carbon has none. And I have another carbon with 2, another carbon with 2, and another carbon with 3. We will be doing the shorthand for the H's, so you won't be drawing all these H's all the time. Because there's no more hydrogens on those 2 carbons, but I know they have to have 4 bonds each, that means I have to have a triple bond here. And if I go to count my bonds around this carbon, I have 1, 2, 3, 4, 1, 2, 3, 4. So it might be helpful to draw these out sometimes when you're naming them. I have one straight carbon chain, no substituents. If I go ahead and number this bad boy to find out how many carbons I have in a row, I have 7 carbons in a row, which is the prefix hept. So I want to assign my suffix. Since I have a triple bond, I'm going to have an -ine ending. I do not have any substituents. Last thing that I need to do is put this all together. So I know I'm going to have heptyne. And in terms of my number, if I number from left to right, starts at carbon 3. The bond is starting going that way from carbon 3. If I go in the other direction, the bond is starting at carbon 4. So I'm going to choose 3 for and have my ordering direction be going from left to right, giving me 3-heptyne. Please pause the video and try these examples on your own. First molecule is pentane. Next we have 2-heptyne. It is important that you number from this direction in order to get the lowest possible number. 2-butene, doesn't matter which way you number from. Propene actually doesn't need a number because you're always starting that bond on carbon 1. 2 and 3 carbon molecules don't give you a lot of flexibility in where you can put a multiple bond, so we're allowed to leave numbers off. If you had put 1 propene though, that would be okay. For ethyl, 2-methyl octane or 2-methyl 4-ethyl octane for your next one. Your substituents are coming off carbon 2 and carbon 4. This is a 1 carbon group, so it's a methyl. 2 carbon group, so it's an ethyl. If we count from here, this is 2,2-dimethyl. You can't call them an ethyl because they're 2 separate branches off of our 5-carbon chain. And yes, you need both numbers, and yes, you need that di. 3,4-diethyl. I have an ethyl here, I have an ethyl here. 1, 2, 3, 4. Diethyl octane. Last but not least, the beast. And again, you could have done 2, 2, 3 trimethyl